Hi there, folks. In this video, we're going to go through the first example problem of a few example problems around energy. In this situation, a kid sleds down a hill with really slick snow. This snow is so slick, in fact, that friction can safely be ignored, and we can still make good predictions about what will happen. This hill is 7.5 meters tall, and the kid and the sled together have a combined mass of 55.0 kilograms. The first thing that we are going to do is sketch this situation, and we're going to annotate our sketch with the given information and a helpful ZRL. That's zero reference level. That's our reference height for gravitational energy. So let's go ahead and make that sketch now. There's our kid with our hill. I drew the kid at the top and the bottom. I drew the ZRL. That ZRL is right around down here. I annotated the height of the hill at moment A, the height of the kid at moment A, the speed and the mass of the kid at moment A, and we don't know the speed of the kid at moment B, and so I left that off. Or I said there's a question mark. We don't know that. But there's a nice sketch of this scenario. I've got a nice visual for what's going on. Next, we're going to model this situation using an energy bar chart. And so I've got our energy bar chart down there at the bottom left. Let's go ahead and first start by defining our system. The system in this case will be the kid and sled, that combo of mass that's moving down the hill. The Earth's gravitational field here is important. And I put the hill in parentheses. It's not wrong to include it, but we also don't need it because it's not an energy giver or receiver. Without friction, it's not giving energy, it's not receiving energy. So we're all good there. We don't need it. Let's talk about what's going to happen in moment A. The energy looks like this. We have a bunch of gravitational energy, but no chemical energy from external pushes, no stretched or compressed thing, no elastic energy, no motion at moment A, so there's zero kinetic energy, and no thermal energy at moment A, because we are always setting our zero reference level for thermal energy to be the first moment we analyze. Now at moment B, our energy situation looks like this. We have a whole bunch of kinetic energy, the kid's in motion, still no chemical energy, still nothing stretched or compressed for elastic energy. We are now at the zero reference height, the zero reference level, so no gravitational energy. And because it's a really slick hill, there was no increase in thermal energy as the kid went down the hill. So overall, we can write an energy conservation equation that says that gravitational energy at moment A must be equal to the kinetic energy at moment B for this closed system. Part C now is going to ask us to compute a prediction, come up with a prediction for how fast that kid will be going, the kid's speed at the bottom of the hill. When I'm doing this part of it, I really encourage you starting with a list of what information is given. What information am I trying to find? This really helps get yourself organized. So I'm reading through the problem again, looking for numbers. I know that the hill has a height of 7.50 meters, so the height of the kid at moment A is 7.50 meters. I know that the kid has a mass of 55.0 kilograms. And it's not explicitly stated, but I'm assuming this kid is doing their sledding on Earth. And so the Earth's gravitational field strength is a known value of 9.81 joules per meter per kilogram. And we are trying to find the speed of the kid at moment B. So now I have a handy list. Always do this every time you're trying to solve a problem in physics. Cool. So let's go ahead and get started now. Got a handy little box here that's going to be where I do my work to solve this problem. And the blue box in the top right is going to tell you which step of our problem-solving method we're on. This is a general problem-solving method that you should always use in physics. Step one is start with some general equation. In this case, that's the general equation from the energy bar chart, our energy conservation equation. The gravitational energy at A equals the kinetic energy at B. We now have a whole bunch of mathematical models which help us describe this energy relationship and all energy relationships. Specifically, we know that gravitational energy can be modeled as mass times gravitational field strength times height. And so I've replaced the purple gravitational potential energy with a purple m times g times h. Similarly, we know we can model kinetic energy as 1/2 the mass times the speed squared. And so I've replaced the blue ke with what's in blue below it, 1/2 mv squared. I've annotated the height with a subscript a to indicate that we're talking about the height of the kid at moment A. And I've annotated the speed and the kinetic energy with a subscript b to indicate that that's the speed of the kid at moment B. Step 2 here is going to be to isolate our find. What is the find? What are we trying to find? It's the VB. So we're going to do some math to get VB on one side of the equal sign by itself. Anytime we have a fraction like 1/2, my first step is going to be to multiply every term by 2. So purple stuff multiplied by 2. Blue stuff multiplied by 2. Be careful, we're not distributing here, 2 to a half, 2 to mass, 2 to v, because we're not adding. These are all multiplied. We want to think of this as one group of stuff, one term. And so when we do this multiplication on the left, 2 times mgh is 2mgh. And 2 times a half mv squared is a whole mv squared. So that's what it looks like after we carry out that multiplication. And now I'm not dealing with fractions, and I'm very happy. The next math step I'm going to do is I notice that we almost have v by itself, but there's this pesky m out front. So I'm going to divide each side by the mass so that we can get rid of the pesky m that's multiplying the thing we're trying to find. And so I'm going to divide each side by m there. And what I notice on the right is if I take mass divided by mass, those divide to 1, which was why I did that to begin with. But if I look on the left side of the equal sign, I notice that there's a mass on top and bottom again. So again, mass divides with mass to 1, and we get that cancellation, leaving us with, on the left side of the equal sign, 2 times the Earth's gravitational field strength times the height at moment A, and that has to be equal to the speed at moment B squared. We are so close to having our find isolated. The last step here is I have v squared, so I'm going to square root both sides. And if I square root both sides, then that should take care of everything. On the left, I'll have square root of 2 times g times h. And on the right side of the equal sign, I'll have the square root of v squared, which is just v. So now I have isolated the thing I'm trying to find, v. And I'm going to look on the other side of the equal sign. Is everything on the other side of the equal sign in my list of givens? 2 is a number, it's an exact number. G is in my list of givens, and the height at A is in my list of givens. Now I'm ready to plug in numbers. Don't plug in numbers before this moment, but do it once you get to this moment where the thing you're trying to find is isolated and the other side of the equal sign is your givens. So I'm going to go ahead and plug all of those numbers in. I switched what was on the left and right of the equal sign. V is now on the left. On the right, we have 2 times the square root of 9.81 joules per meter per kilogram times 7.50 meters. When I go and grab so now we're at the step 3, I should point out, plug in numbers with units. That has to happen after step 2. Now I can grab my handy dandy calculator. I use the Desmos graphing calculator to do this, which is what you see on the screen. I typed this expression all in once into the calculator, and I got this long string of numbers in the end. I encourage you to use a graphing calculator where you can type everything in just like you see it when you write it. But if you're using a regular old-fashioned calculator or more simple calculator, keep your order of operations in mind. But anyways, I see I get 12.1305, blah, 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 blah. Each number in my calculation has 3 sig figs, and 2 is exact. So I should round my final answer to 3 significant figures, put a box around it, and say that speed is 12.1 meters per second. I know it's meters per second because I've been working in SI units, so I should get the SI units for speed. But I do want to double check that. So let's do a unit check real quick. So the unit check. Underneath that square root, I have units of, let's look, no units on 2, units of joules per meter times kilogram with the 9.81, and units of meters with the 7.50. So I've just wrote the units over here. Keep in mind these are units, so that M means meters, not mass. Let's do some simplifying now. I know that a joule is defined as a kilogram times a meter squared per second squared. So I'm going to expand out the joule based on that definition. And now I'm noticing that I have mass dividing with mass. Sorry, I messed that up. Now I have meters divided by meters. I have kilograms divided by kilograms. So all those divide to 1. What I'm left with in the end is the square root of meters squared per second squared, which of course is just meters per second. And so now I'm happy. My units worked out. I know how fast the kid is going at the bottom of the hill. It's 12.1 meters per second. Following the whole problem-solving method as highlighted in the blue box in the top. The last part of this question is going to pop up now. And the last part of this question asks, what would the speed be higher, lower, or the same if this same problem was given to an 85.0 kilogram adult instead of a 55.0 kilogram child, and how do we know? Well, what I'm going to do to answer this question is I'm going to look at where we plugged in numbers, and actually I'm going to go one step higher than that. And what I'm going to notice is that the speed depends on the planet you're on, g, depends on how high up the hill is, but the mass isn't anywhere to be found. And in fact, that's because it divided out a few steps earlier. And because mass is not in the final equation I got for the speed v based on the information I'm given, it must be true that the mass of the person doesn't matter. And so it would be the same speed. Let's think about a physical reason why instead of just a mathematical reason why. So it is the same speed. How come? Mass cancel in the calculation. Or thinking physically, there will be more initial energy stored in the Earth's gravitational field with the adult situation as compared to the kid situation. But that adult also needs to be given proportionally more energy to get up to the same speed as the child. So yeah, there's more energy in the situation with the adult, but you also need to give the adult more energy to get to the same speed. Those things happen in proportion, and so every person will have the same speed at the bottom of the hill. Thank you for learning with me all. I hope it was helpful, and please let me know what questions you have.